In this video, we explain the concept of osmotic pressure using chemical potentials. Alright, so let's begin here with a drawing of what the osmotic pressure is. Suppose that we have a container that looks like this. This is an osmotic pressure device, and we feel it has two compartments, the left compartment and the right compartment. In the left compartment we put liquid A, okay, which is pure, and in the right compartment we're going to put liquid A plus a little bit of solute, which we're going to call B. Okay. The barrier separating these two compartments is does not allow for the passage of either A or B. But we can change the experiment by then making that membrane separating the two compartments semi-permeable. Okay, so this is a semi-permeable membrane now, and it will allow for the passage of A, but not for the passage of B. Okay, so when we actually make this membrane semi-permeable, what will happen is that a little bit of A will actually flow into the right compartment, and you can see that that's the case because there will be a difference in the height of these columns. Okay, again, we know that that is what osmotic pressure will do. And again, remember that this semi-permeable membrane only allows for the passage of A, but not for B. So B cannot move from the right to the left, only A can move from in either direction. And we know the expectation is that A will move from the left to the right. Now we're actually going to try to see what the origin of this is and whether we can actually calculate the value of the osmotic pressure. Okay, the osmotic pressure essentially is the driving force for A to go from the left compartment to the right compartment. Okay, this is what happens when you are at equilibrium. Okay, so this is still A and B. Okay, so at equilibrium, what we know is that the change in Gibbs energy, delta G, should be 0. Okay, the other way to actually write that is to say that the chemical potential of A on both boxes is going to be, has to be identical at equilibrium. Okay. So again, at equilibrium, what we have is the chemical potential of A in the left-hand side of the box is equal to the chemical potential of A in the right compartment of the box. And these are all liquids. Okay. Well, let's try to see if we can actually move this a little forward. Notice that in the left compartment, we only have pure A. So that chemical potential is going to be the chemical potential of A when pure. And in the right compartment, we have A solved with a little bit of B. Okay, so I can A mix with a little bit of B. Right, so if this is an ideal solution, then we can say that that is going to be equal to the chemical potential of A when pure plus RT natural log of X of A. Okay, but because we're working here with colligative properties, we usually write this as 1 minus X of B. Okay, to signify that this is just a property of how much solute you have. Okay, so the question is, well, when does this equality become equal to 0? Or when does the left-hand side of the equation become equal to the right-hand side of the equation? Well, it turns out that if you add any b at all, if that number is not 0, if it's 0.01 or again any number above 0, then it's never going to be the case, looks like, that these two sides of the equation will be identical, right? Because that term is not going to be 0 at any time as long as you have any b. Okay, so it looks like we've come to an impasse, but there's actually an additional contribution to the chemical potential of the right-hand side of the box that we're forgetting. If you think about the pressure at which the left-hand side of the equation is, and the pressure at which the right-hand side of that compartment is, then you will find that it's actually not the same, right? The right-hand side of the compartment has an added hydrostatic pressure from the action of this column of liquid that you don't have in the left-hand side of the box. Okay, this is the height of that column. That will be a hydrostatic pressure. So what we know is that this is going to be equal to, we call that pi. It's going to be equal to the density of the solution, gravity, and then that height. Okay, notice that that is again the hydrostatic pressure that you're under in the right-hand side of the compartment and not in the left. And we also know from prior work that the pressure affects the molar Gibbs energy. Like, we're very familiar with this expression in which we studied how the molar Gibbs energy changes with pressure at constant temperature. Okay, and this is equal to the molar volume of that particular mixture. Okay, so we can see actually by integration of this expression, assuming that the molar volume does not depend on pressure, okay, we arrive at this expression, okay, in which we can see that the molar Gibbs energy, which is no other thing than the chemical potential, okay, does depend on the pressure through the molar volume. Okay, now the change in pressure that we're actually having between the left-hand side and the right-hand side of the equation is simply that hydrostatic pressure, okay, which we'll call pi. Okay, what that means again is that this molar Gibbs energy, okay, that is going to have a new term that is that has to do with the extra pressure that that part of the container is under. So the proper way to write this equation then is this: mu sub A star plus RT natural log of 1 minus x sub B plus, again, the fact that you have an additional contribution to the chemical potential from that hydrostatic pressure, molar volume times that hydrostatic pressure. Okay, great. Now, something interesting before we move forward is that, of course, at equilibrium, the pressure that is driving liquid A from the left to the right-hand side, which is what we call osmotic pressure, and the hydrostatic pressure of this column of liquid, they are equal to each other. Okay, so the way that we're going to measure this osmotic pressure is simply by calculating what is that hydrostatic pressure using that expression. Okay, because at equilibrium they should be the same. All right, so then our goal is going to be to try to solve for this expression, try to solve for the osmotic pressure or the hydrostatic pressure. They are identical in that expression. The first thing that we know is that those two things cancel out, and then we get that this expression turns into minus RT, natural log of 1 minus x sub B is equal to the molar volume times the osmotic pressure. Okay. Now, here we have the natural log of 1 minus the mole fraction of B. If the solution is ideal or ideal dilute, it turns out that the mole fraction of B is going to be a very small number. And it can be demonstrated that this term, okay, is going to be very, very close to minus the mole fraction of B. Okay, and again, that happens when that mole fraction of B is a very small number. Okay, what that means then is that my new expression is going to be equal to plus RT natural log of the mole fraction of B. It's actually not the natural log, but the fraction of mole fraction of B. That's it. Okay, it's equal to the molar volume times the osmotic pressure. Okay, how do we make progress here? Well, we can remember here that the mole fraction of B is equal to the moles of B over the total number of moles in my solution. Okay, in this case it will be the number of moles of A plus the number of moles of B. And the molar volume is just the number of moles total, the volume occupied, okay, by 1 mole of the solution. Okay, so that would be the volume of a solution divided over the total number of moles that I have. Okay, so conveniently, this total number of moles cancel, and then I can solve for the osmotic pressure, okay, by doing the following. It's going to be equal to RT, and then number of moles of B over the volume of the solution, but of course that is the molar concentration. Okay, the osmotic pressure is going to be equal to RT times the molar concentration of the solution. Okay, notice how beautifully simple this expression is. Okay, the osmotic pressure is this linear, depends linearly on the concentration of my solution, okay, of my solid right there. Okay, it's a colligative property because again it depends only on the concentration, not on the nature of that solid that you're adding. Again, notice that we've been able to derive this very simple expression with our knowledge of chemical potentials and so forth. Now, usually the way that we're going to be measuring this osmotic pressure is by calculating the height of this column or measuring that is easy to measure, and then we can calculate with the density of the solution the gravitational constant through that expression. Now, usually the way that we employ osmotic pressure measurements is to determine the molar mass of a particular substance. Okay, so the way that the molar concentration is related to the molar mass is as follows. Notice that the molar mass C sub B, the mass concentration C sub B is equal to the mass of B over the volume of the solution. Okay, and here we have the number of moles of B over the volume. Okay, so those two things are actually related by the molar mass, right? So if I divide here by the molar mass, and I divide here by the molar mass, what I get is that C sub B over the molar mass of B is equal to the molar concentration of B. Okay, that is the relationship between the mass concentration and the molar concentration. So I can come here and say, well, the osmotic pressure is going to be equal to RT, and then the mass concentration over the molar mass. Okay? And this is a great way then to solve for what the molar mass of my substance is. Okay? I can get that the molar mass of my solute is going to be equal to the osmotic pressure over R T and the mass concentration of my solution. Actually, it's the other way around. It's going to be equal to, again, solving for the molar mass, so that is going to be equal to R T, mass concentration over the osmotic pressure. Okay? This is how you can calculate the molar mass of a solute that is unknown using the osmotic pressure device. Okay, so suppose that you're synthesizing a protein in the lab or a polymer, and you don't know exactly what the molar mass of that protein or polymer is. Well, the way that you would do it is prepare a mass concentration of that species, maybe 1 gram per liter, or 2 grams per liter, or 5 grams per liter. Okay, then put it into the osmotic pressure device, measure what the osmotic pressure is through this experiment. You can measure the height, and then utilization of the mass concentration and the osmotic pressure is going to give you directly what the molar mass of that unknown substance is, that polymer or that protein is. Okay, so again, in this video we have explained the origin of osmotic pressure and how it's related to the chemical potential and its application to try to determine the molar mass of solutes and substances.